Welcome once again. In this session, we are going to discuss power spectral density. The power spectral density is simply defined as the Fourier transform of autocorrelation function of input random process xt that is taken as a wide sense stationary process. So, autocorrelation function R function tau and its Fourier transform is S function f, that is called the power spectral density, and mathematically represented as S function f equals to integration of R function tau e to power minus j 2 pi f tau d tau. Now we consider LTI system having impulse response ht with xt and yt as input and output random process. And we know that the output of any LTI system is the convolution of input xt and impulse response ht. So output random process yt equals to integration of h tau x t minus tau d tau. Now after taking expectation on both sides, we get mean of output random process yt. And it is equals to expectation of yt equals to expectation of integration h tau x t minus tau d tau. This mean value of output random process is in time domain. Now in frequency domain representation, LTI system having impulse response capital H function f with input in frequency domain called as power spectral density denoted by capital S function f. Here random process is considered as a wide sense stationary random process. So the output of the LTI system in frequency domain is given as S function f and equals to the product of square of the magnitude of impulse spectrum response and input power spectral density. So S function f is called spectrum of stationary random process yt, and from here we can define a mean square value of output random process yt, which is equals to expectation of y square t, and it is equals to integration of square of the magnitude of hf into power spectral density S function f into df. Also in place of power spectral density of input, we can write integration of R function tau e to power minus j 2 pi f tau d tau. Next we move to the properties of power spectral density of random process xt. In practice, for wide sense stationary random process xt, the power spectral density and the autocorrelation function form a Fourier transform pair. That is, power spectral density S function f equals to integration of R tau e to power minus j 2 pi f tau d tau. That is a Fourier transform of autocorrelation function R function tau. Also, autocorrelation function can be obtained using inverse Fourier transform of power spectral density. So we can say that R function tau equals to integration of S function f e to power j 2 pi f tau df. This Fourier transform pair is called Einstein-Vernier-Khinchin relation. Now, in case of power spectral density, we can find DC response by putting f equals to 0, and it is equals to S naught equals to integration of R tau d tau, which represents the total area under the autocorrelation curve. Next, in the expression of autocorrelation function, we put tau equals to 0, which is called mean square value of input random process xt, and it is equals to R naught equals to expectation of x square t, which is equals to integration of sf df, and this represents the total area under the power spectral density curve. Next, we gather some more information about power spectral density of input random process xt. For this, we again take a stable LTI system in frequency domain. So at the input, we represent power spectral density sf corresponding to random process xt. And here when we treat xt as a real value random process, then the power spectral density having a property of even symmetry. So S function f equals to S function of minus f, which is same as r tau equals to r minus tau. Secondly, in practice, for a wide sense stationary input random process, the power spectral density is called normalized power spectral density. This normalized power spectral density is denoted by capital P function f, and it is the ratio of power spectral density SF upon integration of SF df, which represents the total area under the curve. So normalized power spectral density P function f equals to SF upon integration of SF df. Here we note a point. Normalized power spectral density is always greater or equals to 0, and the area under the curve is unity. Also, the behavior of normalized power spectral density is similar to probability density function. In a stable LTI system, we can also find root mean square bandwidth, and it is determined using normalized power spectral density, as WRMS equals to under root of integration f square pf df. In place of p function f, we can write ratio sf upon integration sf df. And this is the expression of root mean square bandwidth.